Welcome to Still Science Lab. Tonight, we explore a quiet question at the foundation of matter. What if particles are not tiny objects at all? What if the things we call electrons, photons, quarks, and neutrinos are not little balls moving through empty space, but something stranger excitations of deeper fields, events revealed through measurement, stable patterns in an invisible structure beneath everything we call physical? The question sounds simple, but once it is taken seriously, the familiar idea of stuff begins to loosen. Most of us first imagine matter in a very natural way. A stone is made of smaller pieces. Those pieces are made of smaller pieces. Keep going, and eventually we expect to find the smallest pieces of all. Tiny, solid grains, hard and indivisible, moving through space like microscopic versions of the objects we already know. It is an intuitive picture. It feels clean. It feels physical. It gives the mind something to hold. A particle, in this picture, is just a little thing. A smaller stone, a point-like bead, a tiny object with a location, a path, and an identity, moving through a silent background called space. This image has helped science in many ways. It helped early thinkers imagine atoms. It helped physicists model gases, collisions, and the behavior of matter. It still appears in textbooks, diagrams, and ordinary language because it is useful. Sometimes, treating particles as little objects gives good approximations. Sometimes, it lets us calculate, predict, and understand, but it is not the deepest picture we have. Modern physics suggests that particles are not tiny objects in the same way pebbles, planets, or dust grains are objects. They are real, but their reality is not classical. They can leave localized marks in detectors, yet behave like waves in experiments. They can be counted as individual events, yet arise from fields that fill space. They can appear as discrete particles, yet be described by quantum states, probabilities, and interactions rather than simple little paths. The problem is not that particles are unreal. The problem is that the word object comes from the wrong scale. Human intuition was built for the middle world. We evolved among solid surfaces, flowing water, falling stones, moving animals, sunlight, shadows, and distances that could be crossed by foot or sight. We learned a reality of objects. A thing is here, another thing is there. A path connects them. If something moves, it moves through space. If it is not touched, it remains separate. If it has a property, that property belongs to the thing. This classical picture is not false. It is simply incomplete. It is the surface layer of reality, the layer where countless quantum processes have become stable enough to form the world we can live inside. But beneath that surface, the categories shift. Location becomes less absolute. Identity becomes more subtle. Properties depend on measurement. Matter becomes less like tiny furniture placed inside space and more like behavior in fields that space itself contains. An electron, for example, is not a miniature planet orbiting an atomic nucleus. It does not trace a neat classical path around the atom. It exists in quantum states, described by patterns of possibility. When measured, it can be found in a particular place. But before measurement, the best description is not a tiny ball hiding somewhere, waiting to be uncovered. It is a quantum state with structure, probability, and rules. A photon is not a tiny glowing pellet of light. It is the quantum of the electromagnetic field. It can arrive as a single detected event, but light can also spread, interfere, and behave in ways that demand wave-like description. The photon is not fully captured by either everyday image. It is not simply a wave in water, and not simply a bead shot through space. It is something quantum, something that only partly resembles either category. A quark is even more hidden. It is never found alone under normal conditions. It is confined inside protons, neutrons, and other particles by the strong force. To imagine a quark as a tiny separate object sitting inside a proton is already misleading. The proton itself is a dynamic quantum system, filled with quarks, gluons, field energy, and interaction. Its mass comes mostly from the energy of that system, not simply from the bare masses of little pieces inside it. Again and again, the deeper view resists the ordinary image. Particles are real, but they are not small classical objects. They are expressions of fields, states, interactions, and measurement. In quantum field theory, the deeper framework behind modern particle physics, every known particle is associated with a field: the electron field, the photon field, quark fields, neutrino fields, the Higgs field. These fields are not just mathematical decorations placed on top of particles. They are the underlying physical structures from which particles arise. A particle can be understood as an excitation of a field, a ripple, in loose language, a disturbance, a quantized event in something spread throughout space. But even that analogy must be handled carefully. A ripple in water is familiar because water is a substance made of molecules, and the ripple is a motion of that substance. Quantum fields are not water. They are not made of smaller, classical stuff in the ordinary sense. Calling a particle a ripple is helpful only if we remember that it is a ripple in a quantum field, governed by rules unlike the waves we see on a pond. Still, the shift is important. The universe may not be made primarily of tiny things sitting in space. It may be made of fields filling space, with particles appearing as field excitations. This changes the meaning of empty space. Empty space is not necessarily absolute nothingness. In quantum field theory, the vacuum is the lowest energy state of fields, not the absence of fields. Even when no particles are present, the fields remain. They define what particles can appear, how they interact, what forces exist, and what kinds of matter are possible. The void is not simply blank. It has structure. That structure is hidden from ordinary experience because we live in the large-scale result. We do not feel electron fields. We do not perceive quark fields. We do not see the Higgs field filling space. We encounter tables, air, water, skin, metal, light, and sound. We experience the world after the deeper quantum structure has organized itself into stable forms. This is why matter feels so solid. A hand touches a table and meets resistance. The table does not feel like quantum field behavior. It feels like an object. But the resistance comes from electromagnetic interactions, electron states, atomic structure, and quantum rules. The atoms in the hand and the atoms in the table are not little hard balls pressing their surfaces together. They are systems of fields and particles interacting through forces. The experience of solidity is real, but it is emergent. The surface is familiar. The foundation is strange. This is the particle illusion, not the illusion that matter exists. Matter exists. Bodies exist. Stars exist. Stones exist. The world is not a dream. The illusion is that the deepest ingredients of matter must resemble the objects they build. We assume that because large things are object-like, the smallest things must be object-like too. We shrink the world down in imagination and expect the same categories to survive. But nature does not owe us that continuity. The smallest scale may not look like the largest scale, and in fact, it does not. Particles can behave as waves of possibility. They can be entangled, so that the full information of a system belongs to relationships rather than separate pieces. They can appear only as measurement events, leaving detector clicks, tracks, flashes, and energy deposits. They can be created and destroyed in interactions as field energy changes form. They can be identical in a deep way because each particle of a given type is an excitation of the same underlying field. This is not how pebbles behave. Pebbles have surfaces. They have persistent paths. They are made of atoms and can be distinguished by their histories. They occupy space in a way that matches everyday intuition. Particles, at the quantum level, do not simply obey that image at smaller size. An electron detected in one place is not necessarily a tiny object that traveled along one hidden classical route. A photon arriving at a detector is not simply a bead of light that crossed space like a bullet. A particle can have a definite outcome when measured, while its prior quantum behavior requires a broader description. This is why measurement matters. In experiments, particles often appear as localized events. A detector clicks, a track appears, energy is deposited, a flash of light is recorded. These events make particles seem object-like because the evidence appears at a place and time. But the event is not always the whole story. The quantum system before measurement may have been described by a spread-out state, by probabilities, by amplitudes that can interfere. What becomes definite in measurement may not have been a classical object waiting with all properties already fixed. That does not mean consciousness creates reality. Measurement, in physics, is a physical interaction. A particle interacts with a detector. A quantum state becomes correlated with a larger system. A record forms. The result becomes stable enough to be observed, stored, and shared. The strange becomes definite, but the deeper behavior remains quantum. This is where the question becomes larger than particle physics. If particles are not tiny objects, then matter is not built from little solid things in the simple way we imagine. Matter is built from fields, states, interactions, forces, and quantum rules that produce stable structures at larger scales. Atoms emerge, molecules emerge, solids emerge, living cells emerge, worlds emerge. The universe is real, but its reality is layered. The familiar world may be the visible surface of a foundation that does not resemble the surface at all. This should not make reality feel weaker. It should make it feel more profound. A stone is still a stone, but a stone is also a vast arrangement of quantum fields stabilized into matter. A star is still a star, but a star is also a furnace of particles and fields obeying nuclear and quantum laws. A human body is still a body, but it is also chemistry, atoms, electrons, photons, quarks, gluons, and field interactions organized into life. The world does not disappear when we look deeper, it becomes richer. The particle illusion is not a mistake to be mocked. It is a stepping stone. The mind needs images before it can move beyond them. Tiny balls are easier to imagine than field excitations. Solid objects are easier to picture than quantum states. Simple paths are easier than probability amplitudes. But science often begins with useful pictures and then replaces them with deeper ones. The atom was once imagined as indivisible. Then it had structure. The electron was once imagined as a tiny orbiting particle. Then it became a quantum state. Empty space once seemed like nothing. Then it became a vacuum filled with fields. Particles once seemed like the smallest objects. Now they may be better understood as what fields do when energy and interaction take specific quantum forms. This is not the end of the question. It may only be the next layer. Perhaps fields themselves are not final. Perhaps space-time, geometry, and fields emerge from something deeper still. Quantum information, entanglement, hidden symmetries, or principles not yet known. Physics does not yet have a final answer, but it has already shown that the universe is not made of tiny things in the simple way we first imagined. It is made, at least in part, of fields, states, and interactions, and particles are how that deeper structure becomes visible. They are the clicks in the detector, the quanta of light, the stable patterns in atoms, the traces left when fields exchange energy, the small signs of a reality beneath ordinary matter. So what if particles are not tiny objects at all? Then the universe is stranger, but not less real. Matter is not a pile of miniature stones. It is an emergent stability from quantum fields. Space is not empty background alone. It is filled with structures that allow particles to appear. Measurement is not merely passive looking. It is part of how quantum possibilities become recorded facts. And the word particle is not the final description of what exists, but a bridge between what our instruments detect and what our theories say is underneath. The familiar idea of stuff becomes less obvious, but something deeper comes into focus. Reality may not be built from tiny objects moving through empty space. It may be built from fields, states, and interactions from invisible structures that become matter only when the universe speaks in measurable events. We imagine particles as tiny objects because that is how the world first teaches us to think. Before we ever learn physics, before we hear the word atom, before we imagine electrons, photons, quarks, or fields, we learn reality through things we can touch. A stone in the hand, dust in the air, rain on the skin, a ball rolling across the floor, a cup resting on a table, a planet crossing the night sky, moving like a distant object through space. The human mind is trained by surfaces, edges, shapes, locations. A thing is here, another thing is there. A path connects them. If something moves, it moves from one place to another. If something breaks, it breaks into smaller pieces. If those pieces break, we expect even smaller pieces underneath. This is the classical world. It is the world of ordinary intuition, and it is the reason the image of particles as tiny balls feels so natural. When we learn that matter is made of smaller parts, we almost automatically shrink the familiar world down. A rock becomes grains. Grains become molecules. Molecules become atoms. Atoms become smaller ingredients. Somewhere at the bottom, we imagine little solid beads, the final objects, the true pieces from which everything else is assembled. It feels reasonable. It feels physical. It feels like an answer. If a wall is made of bricks, and a brick is made of grains, and grains are made of atoms, then atoms must be made of even smaller bricks. And if matter is solid, perhaps the smallest parts of matter are solid too. The picture is simple, and because it is simple, it has enormous power over the imagination. But simplicity is not always truth. Sometimes, it is only the first shape truth takes when it enters the human mind. The tiny ball picture comes from a deep habit. We explain the unfamiliar by shrinking the familiar. We know how pebbles behave. We know how planets behave. We know how dust floats and drops fall. So when science tells us there are particles beneath matter, we imagine microscopic versions of the objects we already understand. This habit is not foolish. It is useful. It is how thought begins. A child understands a planet as a large ball in space. A student understands an atom as a small center with electrons around it. A beginner understands a gas as tiny particles bouncing in a container. These images are not useless. They help build the first bridge from everyday experience to physical theory. Early science also encouraged this picture. For a long time, atoms were imagined as tiny, indivisible spheres. The word itself comes from the idea of something that cannot be cut further. Matter seemed to be made from small, solid units, too tiny to see, but still object-like in principle. This idea helped explain why substances combine in fixed proportions, why gases behave in predictable ways, and why the world has chemical order beneath its visible complexity. Then the atom was found to have structure. The simple sphere became a system. There was a compact, positive nucleus and negatively charged electrons. This discovery was revolutionary, but it did not immediately destroy the object picture. Instead, it created a new one. The atom became a kind of miniature solar system. The nucleus sat at the center like a tiny sun, and electrons moved around it like planets. The image was memorable. It was elegant. It was wrong in the deepest sense, but it was also useful for a time. It gave people a way to imagine atomic structure before quantum mechanics revealed how strange that structure really is. It captured the idea that atoms have a central nucleus and surrounding electrons. It suggested that atoms are not featureless spheres, but organized systems. It helped move science from one model to the next. That is how models often work. They are not final truth, they are temporary maps. The planetary atom was a stepping stone. It made the invisible feel familiar. It gave a visual form to something no eye could directly see. But electrons are not little planets orbiting the nucleus along neat paths. Atomic structure is not a tiny solar system. Electrons exist in quantum states, described by patterns of probability and energy. They can produce localized measurement events, but their behavior before measurement is not the behavior of tiny classical objects following simple tracks. The old picture helped us climb. Then it had to be left behind. The same happened with the nucleus. A nucleus feels easy to imagine as a compact little ball at the center of the atom. But the nucleus itself is not simple. It is made of protons and neutrons, and those are not simple either. Protons and neutrons are made of quarks and gluons, bound by the strong force in a dynamic quantum structure. Even there, the little ball picture begins to fail. Quarks are never found alone under ordinary conditions. Gluons interact with each other. Much of the mass of a proton comes not from tiny pieces added together, but from the energy of fields and interactions inside it. The deeper we look, the less matter resembles the objects it creates. This is one of the quiet surprises of physics. The familiar world is built from things that are not familiar. At human scale, object thinking works beautifully. It lets us catch a ball, build a house, repair a machine, drive a car, and navigate the world. It lets us understand cause and effect in the everyday sense. It lets us survive. Our brains evolved to track objects because objects mattered. A fruit, a tool, a shelter, a threat, a face, a fire, a stone thrown through the air. The mind is not naturally built to understand quantum fields. It is built to understand things. So when we hear the word particle, we imagine a thing. This is not just a failure of education. It is a deep mismatch between scale and intuition. The quantum world does not announce itself in ordinary life because its strangeness is usually hidden by scale, temperature, interaction, and complexity. The objects around us appear stable and classical because countless quantum events have averaged into the reliable patterns of daily experience. A table does not behave like a single electron. A planet does not behave like a photon. A dust grain does not reveal quantum uncertainty in any obvious way. So our intuition learns the surface, not the foundation. Then physics asks that same intuition to descend beneath the surface, and of course it brings the old images with it. This is why the tiny ball model is so persistent. It is not only wrong, it is comfortable. It gives particles boundaries. It gives them positions. It gives them little paths. It lets us imagine matter as something solid all the way down. It preserves the feeling that reality is made from familiar kinds of things, only smaller. Quantum physics asks for something harder. It asks us to accept that a particle may be real without being a tiny classical object. It may be detected at a point, but not travel like a point object in the usual way. It may behave like a wave in one experiment and produce a localized mark in another. It may be better described as an excitation of a field than as a bead moving through emptiness. It may have properties that are not simply waiting to be revealed, but become definite through physical interaction. This does not mean the early models were failures. They were necessary stages. Science often advances by making pictures that work partly, then discovering where they break. The solid atom gave way to the nuclear atom. The planetary atom gave way to quantum states. Particles as tiny balls gave way to fields, excitations, and measurement events. Each model carried part of the truth, but none could hold all of it. A useful model is not the same as a final picture. That is an important lesson, not just in physics, but in how human knowledge works. We begin with what we can imagine. Then experiments force imagination to change. The world corrects the mind. Reality teaches us where our pictures are too small. The tiny object picture remains useful in some contexts. In particle detectors, scientists often record tracks, collisions, and localized events. In certain calculations, treating particles as point-like entities can work extremely well. In engineering, chemistry, and basic science communication, simplified pictures can guide understanding. The problem begins only when we mistake the picture for the thing itself. A particle can leave a dot in a detector, but that does not mean it was a tiny dot-like object in the classical sense before detection. An electron can be measured in a location, but that does not mean it was orbiting like a little planet. A photon can arrive as one event, but that does not mean it traveled as a tiny glowing pellet through space. The evidence appears object-like because measurements produce definite records, but the underlying quantum behavior is not the behavior of ordinary objects. This is where language becomes difficult. Physics uses familiar words because it has no perfect alternatives. Particle sounds like a small piece. Wave sounds like motion in water. Field sounds like a region spread through space. Each word points towards something, but none fully captures quantum reality. The real structure is mathematical, experimental, and deeper than everyday vocabulary, so we are left translating. We say particle, but we must remember it is not a little stone. We say wave, but we must remember it is not a wave in water. We say field, but we must remember it is not a classical substance filling space like air. Every analogy helps. Every analogy also fails. This is not a weakness of science. It is a sign that science has reached beyond the scale where human intuition was formed. The universe is not required to be easy to picture. It is only required to be consistent with what it does. And quantum physics, strange as it is, predicts what nature does with extraordinary precision. That precision is why the old pictures had to change. Experiments forced the issue. Interference patterns showed that particles could not always be understood as little objects following one simple path. Atomic spectra showed that electrons occupy specific quantum states, not arbitrary orbits. Scattering experiments revealed hidden structure inside protons and neutrons. Quantum field theory showed that particles arise from fields, and that empty space itself is not a simple void. The universe kept saying, smaller does not mean more classical, smaller means stranger. And yet, That strangeness produces the stable world we know. The quantum states of electrons create chemistry. The field nature of particles creates forces. The structure of atoms creates matter. The interactions between particles create light, heat, solidity, and life. The familiar world emerges from an unfamiliar foundation. This is why we imagine particles as objects, because our minds evolved to understand objects, but it is also why we must go beyond that image. The object picture belongs to the world our senses built for us. It belongs to stones, dust, water drops, planets, and visible things moving through visible space. It is a powerful picture because it fits the scale of life. But particles belong to a deeper layer, where the rules are not merely smaller versions of everyday rules. They are different, not irrational, not magical, different. And the history of physics is, in part, the history of learning to let go of images that once felt obvious. The atom is not a solid sphere. The electron is not a tiny planet. The proton is not a simple ball. The particle is not always an object. These realizations do not make reality less real. They make it more layered. Matter is still here. The table is still solid. The planet is still underfoot. The stars still burn. But beneath those facts is a structure that does not resemble the world it creates. The surface is classical. The foundation is quantum. And between them stands the human mind, trying to translate the language of objects into the language of fields, states, probabilities, and interactions. We began by imagining tiny balls because that was the only picture we knew how to shrink. But nature did not shrink the classical world for us. It built the classical world from something deeper. The tiny ball was a beginning, not the answer. The quantum problem with particles begins in a strange place. They leave marks like objects, but they do not always behave like objects before those marks appear. A detector clicks, a screen records a tiny point, a particle track curves through a chamber, an atom absorbs a packet of energy, a photon strikes a sensor. In the final record, the event is definite. Something happened here, not there. One outcome became real enough to measure, store, and compare with theory. This is why particles feel object-like. They seem to arrive at places. They seem to collide. They seem to leave evidence behind. In experiments, the world gives us localized results, and our minds naturally imagine tiny things producing them. A dot on a detector feels like the impact of a small object. A track feels like the path of a particle. A flash feels like a moment of contact. But quantum physics tells us that the record is not the whole story. Before measurement, the behavior of a particle is often described not by a simple path through space, but by a quantum state. That state contains information about possible outcomes. It can spread. It can interfere. It can evolve according to precise rules. It can tell us what results are likely if a measurement is performed, but it does not always describe a tiny classical object traveling along one hidden route. This is where ordinary language begins to fail. A pebble has a path. Throw it through the air, and it moves from one position to another. Even if we do not watch every moment, we assume it was somewhere definite at each point in its motion. A planet orbits a star. Even if clouds hide it from view, we assume it has a definite location, velocity, and trajectory. Objects in the classical world seem to carry their properties with them. They are not waiting for measurement to become object-like. They already are object-like. Particles are different, not because they are unreal, because they are quantum. One of the clearest signs of this difference is interference. When particles are sent through certain experiments one at a time, they can eventually build up a pattern that resembles waves interfering with one another. Each individual detection may appear as a localized point, but the accumulation of many such points reveals structure that cannot be explained by imagining each particle as a little pellet simply choosing one classical path. The particle arrives like a point. The pattern grows like a wave. This is not a small detail. It is one of the central clues that particles do not behave like ordinary objects. A classical object travels one way or another. A quantum system can be described by possibilities that combine, reinforce, and cancel before a measurement occurs. The resulting pattern depends on the structure of the quantum state, not on a simple story of a tiny ball moving through an invisible track. This does not mean the particle is secretly confused. It means our classical categories are too narrow. The words particle and wave come from everyday scale experience. A particle sounds like a grain of sand. A wave sounds like a ripple on water. But quantum systems are not grains of sand or water ripples. They can show features of both, depending on how we interact with them. They can produce discrete events, yet require wave-like mathematics to describe their behavior. The quantum world is not choosing between being a particle and being a wave in the ordinary sense. It is something deeper, and our familiar words catch only parts of it. Another problem is definiteness. In classical life, properties seem to exist whether or not anyone measures them. A ball has a position, a clock has a reading, a stone has a weight, a planet has a speed. Measurement reveals these properties, perhaps imperfectly, but it does not usually create the basic fact that the property existed. Quantum physics complicates this. A quantum system can be prepared in a state where certain properties are not definite in the classical way before measurement. The theory may tell us the probabilities of possible outcomes, but not one pre-existing value for every possible question. When the measurement occurs, a definite result is recorded. Before that, the best physical description may be a state of structured possibilities. This does not mean consciousness is required. It does not mean the universe waits for a human mind to look at it. Measurement in physics means physical interaction. A particle interacts with a detector, a photon is absorbed, an atom changes state. A record forms in the wider environment. The outcome becomes stable enough to count as a fact for practical purposes. The strange part is not that humans are magical observers. The strange part is that physical interaction seems to play a special role in turning quantum possibilities into definite records. That is enough mystery. It does not need exaggeration. Quantum mechanics is often misunderstood as saying anything can happen, or that reality is merely subjective. That is not what the science says. Quantum theory is not a license for chaos. It is one of the most accurate frameworks ever developed. It predicts patterns with astonishing precision. It tells us how atoms behave, how light interacts with matter, how semiconductors work, how lasers function, and why the microscopic world has the structure it does. But its precision does not restore the classical picture. It replaces it. Instead of simple paths, quantum physics gives states. Instead of certainty in every individual event, it gives probabilities. Instead of properties always being definite before measurement, it gives a framework where some properties become definite through interactions. Instead of particles as little objects, it gives quantum systems that can leave object-like traces without behaving like objects all along. This is the quantum problem with things. The world of ordinary things is built from systems that are not thing-like in the ordinary sense. A particle can be detected at a point, but its prior behavior may not be represented by a point moving through space. A particle can carry energy and momentum, but its possible outcomes may be encoded in a quantum state. A particle can interact with another particle, but the interaction may entangle them so that the full information belongs to the combined system rather than either one separately. A particle can seem simple in a detector, while the theory behind it describes fields, amplitudes, and probabilities. The deeper picture is not less real, it is less familiar. This distinction matters because people often hear that particles are not tiny objects and assume the next step is to say particles do not exist. But that is not right. Electrons exist. Photons exist. Quarks exist. Neutrinos exist. Their effects are measurable. Their properties are testable. Their behavior is reliable enough for technology, astronomy, chemistry, and particle physics. Particles are real, but they are not real in the same way a pebble or planet is real. A pebble is an emergent object. It is made of atoms, molecules, crystal structures, defects, surfaces, and countless quantum interactions. At its scale, it behaves classically enough that we can treat it as a definite thing with a definite position. A planet is even larger and more stable. Its quantum nature is hidden beneath mass, gravity, temperature, and constant interaction with its environment. Particles belong closer to the foundation. They do not have to resemble the stable objects they eventually build. This is a recurring mistake of intuition. We expect the smallest pieces of a thing to look like smaller versions of the large thing. Since matter is solid, we imagine its smallest parts as tiny solids. Since objects have paths, we imagine particles with paths. Since everyday properties are definite, we imagine quantum properties as definite but hidden. The experiments say otherwise. Matter's foundation is not simply the classical world made smaller, it is quantum. And the quantum world has rules that do not reduce to ordinary object behavior. This is why the double nature of particles is not just a curiosity. It is evidence that our word particle is a compromise. It points to something that can be counted, detected, and exchanged in interactions. But it does not guarantee a tiny object with a surface and a classical history. A photon can be counted, an electron can leave a track, a neutrino can trigger a rare event. A quark can be inferred from collision patterns. But none of these must be imagined as little beads in the way dust grains are beads. The evidence asks for a different picture, or perhaps not a picture at all. The deepest physical theories are often mathematical before they are visual. We can speak of quantum states, fields, amplitudes, operators, and interactions, but the visual imagination struggles to keep up. That is not a failure of the science. It is a limitation of a mind built from everyday survival. Our ancestors did not need to visualize a wave function. They needed to catch thrown objects, identify solid surfaces, and understand where predators were hiding. Our intuition is classical because life is mostly classical at our scale. Quantum physics reaches beneath that scale. It shows that the familiar world is not the foundation, but an emergence from deeper rules. There is a quiet comfort in this, if we let go of the need for particles to be tiny pebbles. The world is not dissolving into unreality. The table remains solid. The stars remain bright. The body remains material. The planet still turns. Quantum physics does not erase the ordinary world. It explains why the ordinary world can exist from a deeper foundation that looks nothing like ordinary objects. A detector click is real. A quantum state is real in the sense that it governs measurable outcomes. A probability pattern is real in the sense that it appears again and again under repeated experiments. An interference pattern is real in the sense that no classical tiny ball model can fully explain it. Reality is not less because it does not match intuition. It is more subtle. This is also why measurement carries so much philosophical weight. A particle may be described as spread across possible outcomes, yet it leaves one definite mark. The mark becomes part of the classical record. It can be photographed, stored, counted, and discussed. The world we share is made of such records, but the record came from a quantum process whose prior description does not fit the object picture. The classical world may be a world of records. The quantum world may be the deeper source from which records emerge. This does not solve every interpretation problem. Physicists still debate what quantum states ultimately mean. Are they descriptions of knowledge, descriptions of reality, or something in between? Does measurement select one outcome, reveal one branch, or mark the point where quantum information becomes irreversibly spread into the environment? Different interpretations offer different stories, but the experimental facts remain. Particles do not behave like ordinary objects. They create localized detections. They form interference patterns. Their properties can depend on how they are measured. Their behavior is governed by quantum states and probabilities. They are real, but not classical. That is the careful truth. It is strange enough without making it mystical. The universe does not need particles to be tiny solid things in order to build solid matter. It only needs quantum systems whose interactions produce stable structures at large scales. Atoms emerge, molecules emerge, materials emerge. The object-like world emerges from non-object-like rules. A pebble is real, a planet is real, an electron is real too, but they are not real in the same way. The pebble belongs to the classical surface. The electron belongs to the quantum foundation. The planet can be imagined as a thing in space. The electron must be understood through states, fields, measurement, and probability. To force them into the same category is to flatten the universe into a picture too simple for what nature actually does. The particle is not an illusion. The illusion is thinking that a particle must be a tiny version of the objects it helps create. At the quantum level, reality is not made of little classical things moving along hidden tracks. It is made of systems whose possibilities can interfere, whose properties may become definite through interaction, whose evidence appears as localized events, and whose behavior is described by rules deeper than ordinary intuition. Particles are real, but not real like pebbles, not real like planets, real in the quantum way as the hidden foundation from which the world of things finally appears. Beneath matter, there may be something more fundamental than matter itself, not smaller objects hidden inside larger objects, not tiny spheres stacked inside atoms, waiting to be discovered like grains inside grains. Modern physics points toward a stranger foundation, fields that extend through space, fields that can vibrate, interact, carry energy, and appear to us as particles when they are excited in specific quantum ways. This is one of the deepest shifts in the history of physics. For a long time, it was natural to imagine the universe as a collection of objects. Large objects are made of smaller objects. Smaller objects are made of even smaller objects. Keep descending, and eventually, we thought, we would arrive at the final pieces, the smallest things from which everything else is built. But quantum field theory changes that picture. The deeper layer may not be particles inside space. It may be fields filling space. Every known particle is associated with a field. There is an electron field. There is an electromagnetic field, whose quantum excitation is the photon. There are quark fields, associated with the quarks inside protons and neutrons. There are fields associated with neutrinos, with gluons, with the Higgs boson, and with the other known particles of the Standard Model. These fields are not merely abstract labels. They are part of the physical description of reality. A particle, in this view, is not a tiny object placed into the universe from outside. It is often better understood as a localized excitation of an underlying field, a disturbance, a quantum event, a packet of energy and behavior in a field that exists everywhere. This does not mean a field is like air, water, or some invisible fluid. Those analogies can help for a moment, but they are not literal. A water wave is a motion of water molecules. A sound wave is a vibration through a medium. A quantum field is not made of tiny classical pieces in the same familiar sense. It is a deeper physical structure, described by mathematics and revealed through experiment. Still, the comparison gives us a way to begin. A wave on the ocean is not a separate object sitting on top of the water. It is what the water is doing. In a similar but more profound way, a particle may not be an object sitting inside a field. It may be what the field is doing when energy appears in a quantized form. An electron is not simply a miniature bead with a surface. It is an excitation of the electron field. A photon is not a tiny glowing pellet. It is an excitation of the electromagnetic field. A quark is not a little grain trapped inside a proton in the everyday sense. It is an excitation of a quark field, bound through the strong interaction into structures that form the core of matter. This picture is difficult because it removes the comfort of objects. A field is not easy to imagine. It has no edge in the ordinary way. It is not located only here or there. It fills space. It can have values, states, fluctuations, and possible excitations. It can interact with other fields. It can produce particles that appear localized when measured, even though the underlying framework is more spread out and subtle than a tiny solid thing. The universe begins to look less like a box filled with particles and more like a vast set of overlapping fields whose excitations become the particles we detect. This also explains something remarkable. Particles of the same type are truly identical. Every electron in the universe has the same basic properties as every other electron. The electron in an atom in your body, the electron in a distant star, and the electron produced in a particle accelerator are not merely similar objects made to the same design. They are excitations of the same universal electron field. The field is everywhere. The particle is local. This is a powerful reversal of ordinary thinking. We usually imagine that the object is fundamental, and the field is something around it. But in quantum field theory, the field may be more fundamental, and the particle is a particular expression of it. The world of particles becomes a world of events in fields. This idea also changes the meaning of empty space. In everyday language, empty space means nothing is there. No air, no dust, no light, no matter. We imagine a perfect vacuum as a blank region, a kind of pure absence. Remove every particle, and what remains should be nothing. But modern physics does not treat the vacuum as simple nothingness. Even empty space contains fields. The electron field is still there. The electromagnetic field is still there. Quark fields, neutrino fields, the Higgs field, the fields of nature do not vanish just because no particles are present in a region. The vacuum is not the absence of fields. It is the lowest energy state of those fields. That distinction is subtle but enormous. Empty space is not empty in the old sense. It has structure. It has rules. It contains possible excitations. It is the quiet state from which particles can appear when enough energy is supplied. This is why particle accelerators can create particles. They are not pulling tiny objects out of nowhere, like stones from an invisible box. They concentrate energy into a region, and that energy can excite fields. If conditions allow, those excitations appear as particles. The field was already part of reality. The particle is the field made active in a measurable way. The same idea appears in reverse when particles disappear. A particle can decay. A particle and antiparticle can annihilate. Energy can move from one field into another. What vanishes is not reality itself, but a particular excitation. The fields remain. The structure remains. The universe continues to transform through interactions. This is why particles can be created and destroyed without violating conservation laws. In the field picture, particles are not indestructible little bits of substance. They are quantized excitations that can change form according to the rules of the fields and the symmetries of nature. Matter becomes less like a collection of permanent beads, more like stable patterns in a deeper system. Some particles are long-lived, like electrons. Others appear only briefly in high-energy collisions, then decay almost instantly into other particles. Some cannot exist freely under ordinary conditions, like quarks, which are confined inside larger composite particles. Some, like photons, can travel across cosmic distances as light. Each particle type reflects a different field, a different role in the deep architecture of physics. This does not make the world less real. It makes the word real more layered. A particle detected in an experiment is real. The detector click is real. The energy deposit is real. The track is real. But the best explanation of that event may not be a tiny object with a classical history. It may be a quantum field excitation interacting with another quantum system, producing a definite record. The field is real too, but not real like a table, not real like a planet, real as the underlying structure from which particles and interactions arise. This is why quantum fields can feel almost ghostly when described in ordinary language. They are everywhere, yet invisible. They are fundamental, yet not object-like. They can be quiet, yet capable of producing particles. They define the possible behavior of matter, yet they do not show themselves as surfaces or shapes. But their effects are measurable everywhere. Atoms exist because electron fields, electromagnetic fields, quark fields, and gluon fields behave according to precise rules. Chemistry exists because electrons occupy quantum states and interact through electromagnetic fields. Light exists because the electromagnetic field can be excited as photons. Mass is partly connected to the Higgs field, which fills space and interacts with many fundamental particles. The familiar world is not separate from fields. It is made possible by them. A piece of metal, a drop of water, a living cell, a star, all are stable arrangements of field excitations and interactions. The surface feels solid, but beneath it is quantum structure. The object looks still, but inside it are fields, forces, energy, and motion. Matter appears simple because the deeper complexity has become organized. A table is not less real because it is made from fields. It is more astonishing. Its solidity is an emergent result of invisible laws. The vacuum itself may also hold clues to some of the largest mysteries in cosmology. If empty space has structure, then the energy of the vacuum becomes a profound question. Dark energy, the unknown cause behind the accelerating expansion of the universe, may be connected in some way to the properties of space itself. The exact relationship remains unresolved, and it should not be oversimplified. But the fact that empty space is not merely nothing has made the vacuum one of the deepest subjects in modern physics. The smallest framework may touch the largest cosmic question: fields beneath particles, vacuum beneath emptiness, quantum structure beneath the universe's expansion. This is the strange unity of physics. What happens inside atoms may be connected to what happens across galaxies. The same field-based reality that explains particle interactions also shapes our understanding of the early universe, the birth of matter, and the hidden energy of space. In the earliest moments of cosmic history, fields were not quiet background ideas. They were active, extreme, and essential. The universe was hot, dense, and filled with energy. Particles appeared, interacted, transformed, and disappeared as fields exchanged energy. As the universe expanded and cooled, some fields settled into states that allowed ordinary matter to form. Atoms came later, stars later still, life much later, but the fields were there at the foundation. Matter did not appear as solid objects first. It emerged from field behavior. This is why the field picture is so important. It does not merely correct the image of particles. It reframes the universe itself. Reality may not be fundamentally a collection of tiny things moving through space. It may be a network of fields, with particles appearing as local excitations, forces arising from field interactions, and matter emerging as stable patterns in a deeper quantum structure. The old picture asks, what are the smallest objects? The newer picture asks, what fields exist and how do they behave? That question reaches farther. It can include particles, but it is not limited to them. It can explain why particles can be created and destroyed. It can explain why particles of the same type are identical. It can explain forces, interactions, and the strange richness of empty space. It also leaves mystery. Are fields the final layer? Or are fields themselves emergent from something deeper? Quantum information, entanglement, symmetry, or a structure not yet understood? Physics does not have a final answer. Quantum field theory is extraordinarily successful, but it may not be the last word. Gravity still resists full union with the quantum field picture. Dark matter may require new fields. Dark energy may reveal that the vacuum holds secrets we do not yet understand. But even if fields are not final, they are a deeper map than particles as tiny objects. They show that matter is not built the way intuition first imagined. The universe may not be filled with little balls moving through emptiness. It may be filled with fields, layered through space, capable of silence and excitation, invisibility and manifestation, emptiness and creation. A particle is what we notice when a field speaks in a local event. A detector click, a flash, a track, a quantum of light, a stable electron in an atom, a quark bound inside a proton. These are not tiny classical things hiding beneath matter. They are the measurable signs of fields beneath matter. And once that idea takes hold, the world feels different. The space between objects no longer seems like mere absence. The surface of matter no longer seems like the whole of matter. The particles we name no longer seem like final beads of reality. They become openings into something deeper, something spread through the universe, something quiet until energy makes it visible. The deeper layer may not be particles inside space. It may be fields filling space. And what we call matter may be the way those fields become real enough for the universe to touch itself. A particle is not a tiny object with a surface. It is not a microscopic marble, not a bead of matter with a hard edge, not a little planet moving through empty space with a hidden path and a definite shape. Those pictures are easy to imagine, and sometimes they are useful as temporary tools. But they are not the deepest picture modern physics gives us. At the quantum level, what we call a particle is often better understood as an excitation of a field, a ripple in loose language, a vibration, a localized event in a deeper quantum structure that fills space. But even these words must be used carefully. A ripple on water is familiar because we can picture the water, the surface, and the motion. A vibration in a string is familiar because we can imagine the string moving back and forth. Quantum fields are not ordinary water or ordinary strings. They are not made from smaller classical material in the simple way a lake is made of molecules. They are deeper physical structures described by mathematical rules and revealed through experiments. So the analogy is only a doorway. It helps us move away from the idea of particles as little balls. It does not give us a perfect image. The important point is this: in quantum field theory, the field is more basic than the particle. The particle is what appears when the field is excited in a particular quantum way. The universe is not simply a container filled with tiny objects. It may be a vast network of fields, and particles are the measurable events those fields produce. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. Quarks are excitations of quark fields. Neutrinos are excitations of neutrino fields. The Higgs boson is an excitation of the Higgs field. These fields are present throughout space. They do not appear only where a particle is detected. They are part of the underlying structure of reality. When enough energy enters a field in the right way, a particle can appear. When that excitation interacts, decays, or is absorbed, the particle may disappear as a distinct event while the field remains. The field is the deeper continuity. The particle is the localized expression. This reverses the ordinary picture. We usually imagine the world as objects first and fields second. A magnet creates a magnetic field. A charged object creates an electric field. A planet creates a gravitational field. In that everyday way of thinking, fields seem like invisible effects surrounding objects. Quantum field theory asks us to think differently. The fields are not just side effects of particles. The fields are the stage and substance of the particle description. A particle is not something placed into the field like a pebble dropped into a pond. It is more like a stable, countable excitation of the field itself. It is what the field is doing when it carries energy in a specific quantum form. This is why the old image of a particle as a little ball becomes misleading. A ball has a surface. A ball can be painted, dented, rotated, split, and tracked through space. It has a classical body, but an elementary particle does not seem to have a tiny material surface in that sense. An electron is treated, as far as experiments can tell, as point-like in interactions, yet its behavior cannot be reduced to a tiny dot following a classical trajectory. It is detected in places, but described by a quantum state. A photon can arrive at a detector as a single event, but its behavior before detection may require a wave-like description. It can interfere. It can be polarized. It can carry energy and momentum. It can be emitted and absorbed by charged particles. But calling it a tiny pellet of light misses what it truly is in the field picture, a quantum of the electromagnetic field. The electromagnetic field exists throughout space. It is responsible for light, electricity, magnetism, radiation, and the interactions between charged particles. When this field is excited in a quantized way, we can observe a photon. The photon is not a tiny glowing grain moving through a dark container. It is a specific quantum event in the electromagnetic field. The electron field is different, but the principle is similar. The electron field exists everywhere, and what we call an electron is an excitation of that field with the properties of an electron: electric charge, mass, spin, and the ability to interact through the forces allowed by nature. An electron in a hydrogen atom and an electron in a distant galaxy are not two separate manufactured objects that happen to match. They are excitations of the same universal electron field. That matters enormously. It helps explain why particles of the same type are identical. Every electron has the same basic properties because every electron is a manifestation of the same underlying field. There is no factory making electrons with tiny variations. There is no material composition that differs from one electron to another. One electron is not slightly more polished, older, rougher, or more worn than another. Electrons are identical in a deep physical sense. The same is true of photons. The same is true of quarks of the same type. The same is true of other elementary particles. This sameness is one of the quiet miracles of physics. The universe is filled with repeated excitations of universal fields. The electron in your body is not merely similar to an electron in a star on the far side of the galaxy. It belongs to the same field, governed by the same rules, carrying the same fundamental properties. The local particle is temporary. The field is cosmic. This gives matter a strange unity. The objects around us look separate. A stone is different from a leaf. A body is different from a star. A planet is different from a cloud of gas. But at the deepest tested level, all of them are built from excitations of the same underlying fields. The universe repeats its fundamental patterns everywhere. A particle, then, is not just a little piece of stuff. It is a way a field becomes countable. It is a quantum event with identity, energy, and interaction. It is a local appearance of a structure that is not local in the ordinary sense. This also explains why particles can be created and destroyed. If particles were tiny permanent balls, creation and destruction would feel almost magical. Where does the ball come from? Where does it go? But in the field picture, the answer becomes clearer. A particle appears when energy excites a field. It disappears when that excitation is absorbed, transformed, or converted into excitations of other fields, according to the laws of conservation. In a particle accelerator, energy can be concentrated into a tiny region. That energy can excite fields and produce particles. Some of those particles may exist for only a brief instant before decaying into others. The detector does not observe tiny objects pulled from hidden storage. It observes the results of fields being excited, interacting, and transforming. This is why high-energy physics often feels like listening to fields speak through debris. The collision happens. Fields respond. Particles appear. Particles decay. Tracks, flashes, and energy deposits reveal what took place. The particle is not always a lasting object. Often, it is an event, a brief expression of underlying fields. This does not make particles less real. A wave on the ocean is real, even though it is not a separate object from the water. A sound is real, even though it is not a little thing flying through air like a pebble. A flame is real, even though it is a process rather than a solid object. In a deeper and more precise way, particles are real as quantum excitations. Their reality is not the reality of tiny classical solids, it is the reality of field events. The problem is that our language was not built for this. The word particle carries the memory of dust, grains, and fragments. It suggests something small and solid. The word excitation sounds abstract, almost less real. But in modern physics, the excitation is what corresponds to what experiments detect. The abstraction is not a retreat from reality. It is a better match to what nature actually does. The world at the foundation is not less concrete because it is harder to picture. It is simply not classical. Quarks make the point even more sharply. Quarks are excitations of quark fields, but they are confined by the strong force. They do not appear alone under ordinary conditions. Inside protons and neutrons, quarks exist as part of a dynamic system with gluons and field energy. The proton is not a bag containing three little balls in any simple sense. It is a stable quantum structure, a bound state of fields and interactions. Most of the proton's mass comes not from the small bare masses of its quarks, but from the energy of the strong interaction inside it. The mass of ordinary matter is therefore deeply connected to the behavior of fields, not merely the combined weight of tiny parts. This is another reason the little ball image fails. If matter were built from hard beads, we might expect mass to be the sum of bead masses. But in the quantum field picture, energy, confinement, interaction, and field dynamics become central. Matter's substance is not just material pieces, it is organized field energy. The more carefully we look, the more the universe refuses to be made of miniature furniture. Particles also do not always have simple locations before measurement. When a particle is detected, it leaves a localized record, but the quantum state that led to that record may have been spread out, capable of interference, governed by probabilities. The particle-like event is real. The field-like evolution is real. The challenge is that neither picture alone is the whole truth. A particle is the point where our instruments catch the field in action. A detector click can make the event seem simple. Something arrived, something hit, something happened here. But behind that simple record is a deeper process. Fields interacting, quantum states evolving, probabilities becoming outcomes. The particle is not a tiny object with a surface. It is a quantum event in a field. That sentence is difficult because it asks us to abandon the visual comfort of smallness. Small is not the same as simple. A particle may have no internal structure we can measure, and yet its behavior may be governed by field theory, symmetry, probability, and interaction. It may be elementary, but not classical. It may be point-like, but not a tiny ball. This is the strange balance modern physics asks us to hold. Particles are countable. They can be detected. They carry energy. They interact. They build matter. But they are not little solid things. They are excitations of fields that fill space. Once this idea takes hold, the universe begins to feel different. Empty space no longer feels like mere absence. It contains the fields whose excitations become matter and light. Matter no longer feels like a pile of tiny objects. It becomes a stable arrangement of field excitations and interactions. Forces no longer feel like invisible strings between little balls. They become field behavior, carried and shaped by quantum rules. Reality becomes less like a machine made of parts and more like a vast physical language made of fields and events. A photon is the electromagnetic field speaking as light. An electron is the electron field appearing as matter. A quark is a quark field bound into the hidden core of atoms. The same fields stretch across the cosmos, allowing the same particles to appear in laboratories, stars, galaxies, and the early universe. This is why particle physics is also cosmic physics. The particles studied in accelerators are not artificial inventions. They are excitations of the same fields that filled the young universe, shaped the formation of matter, and still operate inside every atom. To understand a particle is to understand a way the universe can express itself. The field picture also leaves room for mystery. Are the known fields all there is? Dark matter may require new fields. Inflation, if it occurred, may involve fields not yet directly observed. Dark energy may be connected to the vacuum in a way we do not yet understand. Gravity remains difficult to fit into the same quantum field framework completely. Fields may be the deepest layer we know how to describe, but not necessarily the final layer of reality. Still, they have already changed the meaning of particles. The old question was, what are the smallest things? The deeper question is, what are the fields, and what excitations can they support? That is a more powerful way to think. It explains why particles are identical, why they can be created and destroyed, why empty space is not simply nothing, and why matter is tied to invisible structures that fill the universe. A tiny ball exists in space. A quantum excitation belongs to a field that defines what can happen in space. That is the shift, and it is not only technical. It changes the emotional shape of matter. The world we touch becomes the surface of something more subtle. The solidity of a table, the light of a star, the chemistry of a cell, the energy of a particle collision, all become expressions of fields beneath the visible world. The universe may not be made of tiny objects. It may be made of fields that become particle-like only when energy, interaction, and measurement give them local form. A particle is not a miniature thing hiding inside matter. It is a moment when a field becomes definite enough for the universe to leave a trace. A particle begins to look like an object when it leaves evidence. Before that moment, the story is much harder to picture. In the classical world, measurement feels simple. A stone has a position before we look. A planet follows an orbit whether or not anyone is watching. A ball flying through the air has a path even if no camera records it. Measurement, in this ordinary sense, reveals what was already there. It does not seem to participate in making the world definite. It only tells us what the world was already doing. But quantum physics does not allow us to carry that picture downward without change. At the quantum level, a system may be described by a state, not by a tiny object with a neat path and a complete list of definite properties. That state contains possible outcomes. It gives probabilities. It tells us what can be found if a measurement is made, and how likely different results are. But it does not always describe a little thing traveling through space in the way a pebble travels through the air. Then measurement happens. A physical interaction occurs. A detector clicks. A track appears in a chamber. A flash of light is produced. Energy is deposited in a sensor. An atom changes state. A mark is made. A record forms. Suddenly, the strange becomes definite. Something happened here. Something was measured with this energy. Something produced this result, not another. This is why particles can seem like tiny objects. We do not usually encounter the quantum state directly. We encounter the evidence left after interaction, and that evidence is often localized. It appears at a place. It arrives at a time. It enters the world as a specific record. A dot on a detector feels like the impact of a small object. A curved track feels like the path of a particle moving through space. A flash feels like a tiny collision. The evidence looks classical, so our imagination fills in a classical story. We imagine a little object traveling through space, carrying all its properties, then striking the detector and revealing itself. Sometimes that picture works well enough as a rough description, but at the deepest level, it can mislead us. The thing being measured may not have behaved like a classical object before the detection. Its earlier behavior may have required a quantum description, a state, a field excitation, a set of possibilities, an evolving probability structure. Measurement is where that hidden quantum description becomes a visible fact. This does not mean a human mind creates reality. That idea is often repeated, but it is too careless. In physics, measurement does not require a conscious observer staring at an experiment. Measurement is a physical process. A quantum system interacts with a larger system in a way that produces a stable record. The detector absorbs energy. The environment becomes involved. Information is amplified into something macroscopic. The result becomes difficult, often practically impossible, to reverse. The record is what matters. A measurement is not merely looking, it is interaction plus a trace. A photon hitting a sensor can be a measurement. An electron leaving ionization behind in a detector can be a measurement. A particle depositing energy in a material can be a measurement. A quantum system becoming entangled with a large environment can help produce the appearance of a definite outcome. The world does not wait for human eyes. It becomes classical looking through physical interactions. Still, the mystery remains. Before the record, quantum theory may describe multiple possible outcomes. After the record, there is one outcome in the shared classical world. Before measurement, the system is described by probabilities and quantum states. After measurement, the laboratory notebook contains a number. The detector contains a mark. The data file contains an event. This transition is one of the deepest puzzles in physics. It is not a puzzle because the theory fails. Quantum mechanics works with extraordinary precision. It predicts the results of experiments. It explains atoms, lasers, semiconductors, magnetic resonance imaging, particle interactions, and the structure of matter. The puzzle is not practical weakness, the puzzle is meaning. What exactly is a quantum state? What exactly happens when a measurement produces one result? Does measurement reveal a property that already existed? Does it create the definite outcome through interaction? Does the wave-like description represent physical reality, or only our knowledge of possible results? Different interpretations answer these questions differently, and physicists still debate them. But the experimental lesson is clear. Particles look like objects when they leave evidence. Their deeper behavior is quantum. Consider the way a particle track appears. In a detector, a charged particle may pass through material and leave a trail of interactions. To the eye or to an instrument, the track looks like a path. It invites the image of a tiny object moving through space, like a bullet through fog. And in some cases, for a high-energy particle interacting repeatedly, that image can be a very useful approximation. But even that track is not the direct sight of a little solid ball. It is a chain of measurement events. The particle interacts here, then there, then there. Each interaction leaves evidence. The sequence becomes a track. The track is real, but it is built from records. It is the history of interactions between a quantum system and a measuring environment. What looks like a continuous classical path is often a reconstruction from discrete physical traces. In other experiments, the object-like picture fails more dramatically. A single photon or electron can be sent toward an arrangement that allows interference. Each detection still happens at one location, one click, one mark, one recorded event. But after many repetitions, the pattern that emerges cannot be explained by simple little objects taking ordinary paths. It reflects the evolution of the quantum state before measurement. Each event is localized. The pattern is wave-like. The particle seems object-like at the moment of detection, but its deeper behavior before detection cannot be understood as merely object-like. This is one of the great lessons of quantum physics. The event and the state are not the same kind of thing. The event is the definite result we record. The state is the structured description that gives possible results and probabilities. We often mistake the event for the entire nature of the particle, because events are what we observe most directly. But the universe may be doing something subtler between events. A detector click is not a window into a tiny, solid object. It is the moment when a quantum process becomes a recorded fact. That fact can be counted. It can be analyzed. It can be repeated statistically. It can be used to infer the particle's energy, momentum, charge, or identity. But the fact does not necessarily prove that the particle was a little classical thing all along. A fingerprint proves something touched a surface. It does not tell the entire story of what that something was before contact. In particle physics, much of what we know comes from traces. Short-lived particles may decay before they ever reach a detector. Scientists infer them from the particles they become. A Higgs boson, for example, is not seen directly as a tiny object flying through space. Its existence is reconstructed from decay products and statistical patterns. Quarks are not isolated under normal conditions, but their behavior is inferred from jets and scattering. Neutrinos rarely interact, but when one finally does, its faint trace can reveal its passage. The particle world is forensic. It is built from evidence left after interactions. The evidence is real, and the particles are real. But reality here is not the everyday reality of a marble rolling across a table. It is the reality of quantum fields, possible outcomes, interactions, and records. What we call a particle may be a localized excitation of a field. What we call a detection may be that excitation interacting with matter in a way that leaves a stable trace. The trace looks like an object. The underlying process is not so simple. This is why measurement creates such a deep bridge between the quantum and classical worlds. On one side is the quantum description: states, amplitudes, probabilities, superpositions, entanglement, fields. On the other side is the classical record: a number, a mark, a click, a flash, a photograph, a line of data. Science lives at the boundary between them. It uses classical records to infer quantum behavior. That boundary is not imaginary. It is the place where experiments happen. A detector is built from ordinary matter. It has atoms, electronics, temperature, noise, and structure. When a quantum system interacts with it, the result becomes amplified into a macroscopic signal. Something too small and strange for direct human experience becomes something a computer can record and a scientist can analyze. The quantum world speaks through measurement, but it speaks in translated form, and every translation carries risk. The localized result tempts us to imagine a localized object. The track tempts us to imagine a tiny path. The click tempts us to imagine a bead striking a surface. These images may help at first, but they cannot be the full explanation. If they were, quantum interference, entanglement, and measurement behavior would not look the way they do. A particle is not simply what appears at the end of an experiment. It is also the quantum system that led to that appearance. This distinction protects us from two opposite mistakes. The first mistake is to say particles are just tiny classical objects because they leave object-like evidence. The second mistake is to say particles are not real at all because they do not behave like classical objects. Both are too simple. Particles are real. Their detections are real. Their effects are real, but their reality is quantum, not classical. They are not little stones with hidden surfaces. They are not miniature planets with definite orbits. They are not simply dots moving through empty space. They are described by states and fields, and they become object-like to us when physical interactions produce definite records. The world we experience is full of such records. Every image, every sound, every touch, every measurement of temperature, pressure, position, and light depends on physical interactions becoming stable enough to matter at our scale. The classical world is a world where records are robust, objects persist, properties seem definite, causes leave traces. The environment constantly interacts with systems, suppressing delicate quantum behavior and making reality appear stable. That stability is not fake, it is emergent. The quantum strangeness does not vanish. It becomes hidden beneath layers of interaction. A table appears solid because countless quantum systems form stable atomic and molecular structures. A beam of light appears continuous because immense numbers of photons and field interactions create a smooth experience. A detector event appears as a clean click because a microscopic interaction has been amplified into a macroscopic record. Measurement is how the strange becomes usable. It is how quantum possibility becomes data. It is how fields and states become facts in the laboratory. There is something quietly profound about this. Reality, at the deepest levels we can probe, may not be made of finished objects waiting to be revealed. It may be made of systems that become definite through interaction. The universe may not be a collection of tiny things with all properties written on them in advance. It may be a process in which possibilities, governed by strict laws, produce records when physical systems meet. This does not make reality subjective. It makes reality relational, in a precise physical sense. What is measured depends on the interaction. What becomes definite depends on the experimental arrangement. The quantum state gives the structure of possible outcomes. The measurement produces one recorded result. The result is not arbitrary, but neither is it always predictable in the classical way. A particle leaves evidence like an object, but its deeper nature is revealed by the pattern of evidence across many measurements. That is why repeated experiments matter. One detector click tells us that one event happened. Many clicks reveal a distribution. One point may look random. Thousands of points reveal interference. One rare detection may be noise. A statistical excess may point to a new particle. Quantum physics often speaks not through single events alone, but through patterns formed by many events. The single event becomes definite. The pattern reveals the quantum law. This is the rhythm of the microscopic world. Possibility, interaction, record, pattern, not chaos, not magic. A disciplined uncertainty that becomes measurable reality through experiment. Particles appear object-like because our instruments catch them at the moment they make a mark. But between marks, before marks, beneath the marks, the language of tiny objects is too simple. The particle may be an excitation in a field. Its behavior may be described by probabilities. Its properties may not all be definite before measurement. Its identity may be tied to the universal field from which it arises. The object is the evidence. The quantum system is the deeper story. And this is why the idea of particles as things becomes unstable. At the human scale, things are stable objects with surfaces and paths. At the quantum scale, what we call things may be patterns of interaction, excitations, and measurement outcomes. The world of objects is real, but it may not be fundamental. It may be what quantum reality becomes when records are stable enough to form a shared world. A detector click is a tiny moment of translation, a flash in matter, a mark in time. A quantum possibility becoming a classical fact. Particles look like objects when they leave evidence, but their deeper behavior is quantum, and in that difference, the universe reminds us that what appears definite on the surface may come from a foundation far stranger than the surface can reveal. If particles are not tiny objects, then the meaning of matter changes. Not because matter becomes unreal, not because the world dissolves into imagination, but because the foundation beneath the world is not made of little solid pieces in the way our senses first suggest. The table is still solid, the ground is still firm, a star still burns, a living body still breathes, moves, and feels. But the deeper explanation for these facts is stranger than the facts themselves. Matter is real, but its foundation is not intuitive. At the surface of experience, the world appears to be built from things. Objects have boundaries, shapes, locations. A stone has an edge. A drop of water has a surface. A planet occupies a region of space. A human body seems continuous, stable, and separate from the air around it. This object-like world is the world our minds were built to navigate, but modern physics asks us to look beneath that surface. And underneath, matter stops looking like a pile of tiny things. Particles are not little balls stacked together until they become atoms, molecules, rocks, and bodies. They are quantum excitations, field events, states, and interactions. Electrons do not orbit nuclei like planets. Photons are not tiny glowing pellets. Quarks are not ordinary grains hidden inside protons. The smallest ingredients we know do not behave like miniature versions of the world they create. This is a profound reversal. The familiar world is built from an unfamiliar foundation. Solidity, for example, feels like one of the most basic properties of matter. Put a hand against a wall, and the wall resists. Stand on the ground, and the ground holds you. Pick up a stone, and it has weight and surface. The body understands solidity before the mind understands language. But solidity is not the result of tiny hard particles pressing directly against tiny hard particles. At a deeper level, it comes from quantum fields, electromagnetic interactions, electron states, and the rules that govern how matter can be arranged. When your hand presses against a table, the atoms in your hand and the atoms in the table do not merge into one another. Their electrons and fields interact. Quantum rules resist certain configurations. Electromagnetic forces respond. The result, at human scale, is the sensation of touch. The solidity is real, but it is emergent. It is not fundamental in the simple way it feels. Shape is similar. An object has a form because its atoms and molecules are arranged in stable patterns. Those patterns are held together by electromagnetic interactions, quantum bonding, and the structure of matter at scales far below visibility. The shape of a crystal, the flexibility of a leaf, the hardness of metal, the flow of water, the softness of skin, each comes from the behavior of atoms and molecules, and those come from deeper quantum rules. The world has form because quantum systems can organize. Chemistry depends on the same hidden foundation. The behavior of electrons around nuclei determines how atoms bond, react, share energy, and form molecules. Carbon can build long chains and complex structures because of its electron configuration. Water behaves as it does because of the arrangement and interaction of its atoms. Proteins fold. DNA stores information. Cells maintain themselves through controlled chemical processes. All of this rests on electrons, fields, and quantum states. Without quantum rules, chemistry would not be chemistry. And without chemistry, matter would not become life. So the strange foundation is not remote. It is not limited to particle accelerators or equations. It is inside every object, every breath, every biological process, every technological device. The world we experience is the stable result of quantum behavior repeated across countless systems. That is what emergence means. Emergence does not mean illusion. It means a higher level reality arising from deeper rules. Temperature is a familiar example. A cup of warm tea has a temperature. That temperature is real. It can be measured. It affects the body. It changes the behavior of matter. But temperature is not a tiny substance inside the tea. It emerges from the motion and energy of many particles. At the level of one particle, temperature is not the same kind of property. It becomes meaningful when many microscopic degrees of freedom are considered together. Solidity works in a similar way. Shape works in a similar way. Chemistry, materials, and ordinary objects emerge from deeper patterns. The world is not fake because it emerges. A wave is real, even though it is a pattern in water. A sound is real, even though it is a vibration moving through matter. A flame is real, even though it is not a solid object but a process. Life is real, even though it emerges from chemistry. Conscious experience is real to the beings who have it, even though it depends on physical systems far beneath awareness. Reality has layers. The mistake is thinking that only the bottom layer is real. The table is real at the level of tables. The atom is real at the level of atoms. The electron is real at the quantum level. A field is real in the framework that describes particle behavior. These layers are not enemies. They are different descriptions of the same universe, each one useful at a different scale. But the deeper layer changes how we understand the surface. If particles are not tiny objects, then matter is not a simple collection of little solid pieces. It is a stable organization of quantum fields and interactions. The everyday world is not the direct appearance of tiny classical things. It is the large-scale result of non-classical rules. This does not make the world less trustworthy. It makes intuition less final. A pebble remains a pebble. But the pebble is not made of smaller pebbles all the way down. Its surface, hardness, color, weight, and stability arise from atoms, electrons, nuclei, fields, and forces. What looks simple from the outside becomes deeply structured underneath. A planet remains a planet, but it is not a single solid thing in the deepest sense. It is an enormous gravitationally bound system of matter, energy, heat, chemistry, pressure, fields, and motion. A star remains a star, but its light and life come from nuclear processes, particle interactions, plasma behavior, gravity, and radiation. The familiar objects of the universe are real patterns, not illusions, patterns. And patterns can be physically real. This changes the philosophical meaning of reality because it breaks the assumption that reality must resemble human-scale objects at every level. The universe is not obligated to be object-like all the way down. It is not required to match the categories the brain evolved to use. Our minds are excellent at recognizing faces, tracking motion, avoiding danger, holding tools, and navigating surfaces. They are not naturally built to visualize quantum fields. So when quantum physics feels strange, that strangeness is not necessarily a sign that nature is irrational. It may be a sign that intuition was trained on the wrong scale. The deeper world is not vague. It is precise. Quantum physics may be difficult to picture, but it is extraordinarily successful in prediction. It explains atomic spectra, chemical bonding, semiconductors, lasers, particle interactions, and many of the technologies that define modern civilization. The theory works not because it satisfies common sense, but because it matches nature. That is a humbling lesson. Reality is not limited by what feels obvious. The particle as object image feels obvious because it is close to the world we experience. But nature has shown that obviousness is not the same as truth. The earth feels still. yet it moves. Space and time feel separate, yet relativity joins them. Matter feels solid, yet solidity arises from quantum interactions. Empty space feels empty, yet fields remain. Particles feel like little things, yet they may be excitations in fields. Again and again, science does not destroy reality, it deepens it. The old pictures are not always worthless. They are stepping stones. Treating particles as little objects can help in certain contexts. Atoms as small spheres can help with chemistry at a basic level. Electrons around nuclei can be introduced with simplified diagrams. Particle tracks can be described as if small things moved through detectors. These images allow the mind to begin, but they are not the final picture. If we stop at them, we mistake a teaching tool for reality. That is why this shift matters. It changes the way we understand matter, but also the way we understand knowledge. Science does not simply confirm intuition. It trains intuition to become more subtle. It teaches us when a picture is useful, when it fails, and when a deeper framework is needed. The deepest truths may not be visual. They may be structural. They may be patterns of fields, symmetries, probabilities, and interactions that do not resemble ordinary objects, but still govern the ordinary world with remarkable precision. This also changes how we think about ourselves. The human body feels continuous and personal. It is warm, breathing, alive. Yet it is made of atoms, molecules, fields, and quantum interactions. The chemistry of life depends on electrons. The mass of matter depends largely on energy inside protons and neutrons. The light we see arrives as photons. The nervous system depends on physical signals and molecular structures. We are not separate from the strange foundation. We are made from it. This does not reduce human experience to something meaningless. It places experience inside a deeper cosmos. The matter that thinks about quantum fields is itself built from quantum fields. The mind that asks what particles are emerges from atoms whose behavior depends on the very rules being questioned. There is a quiet circular beauty in that. The universe becomes aware of its own hidden structure through arrangements of that same structure. If matter is an emergent surface, then we live on that surface. We touch it, breathe it, build with it, love within it, and use it to ask questions about what lies beneath. The fact that the surface emerges does not make it less meaningful. It makes it more astonishing that such a stable, rich, life-bearing world can arise from quantum foundations that look nothing like everyday objects. The familiar world is not the opposite of the quantum world. It is what the quantum world becomes at our scale. This is why the meaning of reality changes. Reality is no longer a single-layer inventory of things. It becomes a hierarchy of descriptions, each one connected to the others. Fields produce particles. Particles form atoms. Atoms form molecules. Molecules form materials. Materials form planets, oceans, cells, machines, and minds. At every level, new patterns appear, and each pattern is real in its own way. Matter is real, but its foundation is stranger than matter itself appears. That is the careful, powerful conclusion. We do not need to say the world is illusion. We do not need to say particles are imaginary. We do not need to turn physics into mysticism. The truth is already profound enough. The object-like world is an emergent surface built from quantum rules that are not object-like. The surface is stable. The foundation is strange. And both are part of reality. A particle is not a tiny object with a surface. It is a quantum event in a field. Matter is not a pile of microscopic pebbles. It is organized field behavior, structured by forces and interactions. The classical world is not false. It is the large-scale face of a deeper quantum order. This is where science becomes more than measurement. It becomes a change in perspective. The world you touch is still there, but beneath the touch is a hidden architecture. Beneath solidity is interaction. Beneath shape is structure. Beneath chemistry is quantum law. Beneath ordinary objects is a reality that refuses to be reduced to ordinary objects. The universe is not less real because its foundation is strange. It is more profound because the familiar world rises from something deeper than familiarity itself. Matter is stranger than it looks. That may be the most honest conclusion modern physics offers. Not that matter is unreal, not that particles are illusions, not that the world around us is only a trick of perception. The table is still solid enough to hold a cup. The ground is still firm beneath the body. Stars still burn, atoms still bond, light still travels. The universe remains physical, measurable, and real. But the foundation beneath that reality is not as simple as it first appears. Particles are not illusions. They leave evidence. They carry energy. They interact. They can be counted, measured, scattered, absorbed, emitted, and detected. A photon can strike a sensor. An electron can leave a trace. A proton can be accelerated and collided. A neutrino can rarely, quietly, touch matter after passing through almost everything else. The particle world is not imaginary. It is one of the most precisely tested parts of science. And yet particles are not tiny classical objects either. They are not little balls with surfaces. They are not miniature stones moving through empty space. They are not small versions of the familiar things they help create. An electron is not a bead. A photon is not a glowing pellet. A quark is not a grain hidden inside the nucleus. The deeper physics does not support that simple image. A particle is better understood as something quantum, an excitation of a field, a state with possible outcomes, a pattern of interaction, a localized event when measurement produces a record. This is difficult because our language was not built for it. Our words come from the surface of reality. We say object because we live among objects. We say particle because we imagine small pieces. We say wave because we have seen water move. We say field because we need a word for something spread through space. But every one of these words carries human-scale baggage. The universe is under no obligation to fit the pictures inside our words. Our everyday language was built for stones, tools, bodies, rivers, fire, distance, weight, and motion. It was built for survival inside the classical world. It was not built for quantum fields. It was not built for superposition. It was not built for entanglement, probability amplitudes, particle creation, or measurement. So when we speak about the foundation of matter, we are always translating, and every translation is incomplete. That is why scientific humility matters. Physics has not failed when it becomes hard to picture. It has reached beyond the scale where ordinary intuition was trained. The goal is not to force the universe into comfortable images. The goal is to listen carefully enough that the images can change. For centuries, matter seemed obvious. Something solid was made of stuff. Break the stuff down, and eventually there must be smaller stuff. Break that down, and eventually there must be smallest stuff. This picture feels so natural that it is hard to see it as a picture at all. But nature has shown us something deeper. Atoms are not solid spheres. Electrons are not planets around nuclei. Protons are not simple balls. Particles are not tiny objects in the classical sense. And empty space is not simply empty. The deeper we look, the less reality resembles the surface it creates. That does not make the surface false. it means the surface is emergent. Solidity emerges from electromagnetic forces, quantum rules, and the structure of atoms. Shape emerges from molecular arrangements and interactions. Chemistry emerges from electron states and bonding. Ordinary objects emerge from matter organized across enormous numbers of quantum systems. The familiar world is real, but it is not fundamental in the way it feels. It is the stable face of deeper activity. A table feels still, but inside it, atoms vibrate, electrons occupy quantum states, fields interact, and forces maintain structure. A human body feels continuous, but it is made of cells, molecules, atoms, particles, and fields, organized in a pattern that is constantly exchanging energy and matter with the world around it. A star looks like a glowing sphere, but it is a gravitationally bound plasma, powered by nuclear processes and radiating photons into space. At every level, reality has a description, and no single level owns the whole truth. The table is real as a table. The atom is real as an atom. The electron is real as a quantum excitation. The field is real as the deeper structure that allows the electron to exist. These are not competing realities. They are layers of one reality seen at different scales. The mistake is to demand that the deepest layer look like the surface layer. It does not. Matter is not made of little solid pieces in the way a wall is made of bricks. It is made from quantum fields and interactions that produce stable patterns. The word made itself becomes delicate. A particle may be an excitation, not a tiny ingredient with a surface. A force may be a field interaction, not an invisible string. A measurement may produce a definite record, even though the quantum system before measurement was described by possibilities. The world of objects is what quantum reality becomes when it is stable enough, large enough, and entangled enough with its environment to behave classically. This is not less real, it is more layered. A wave is real, though it is not separate from water. A sound is real, though it is a vibration through matter. A flame is real, though it is a process rather than a solid thing. In the same way, ordinary matter is real, even if its foundation is made of fields, states, and interactions rather than tiny classical objects. Reality does not require simplicity to be real. It only requires consistency. And quantum physics is astonishingly consistent. It predicts atoms, spectra, chemical behavior, lasers, semiconductors, particle collisions, and countless technologies with extraordinary precision. The strange foundation is not a vague idea, it is a working framework. It is strange because it is deeper than intuition, not because it is weak. This is one of the quiet lessons of science. The universe often becomes more real when it becomes less familiar. The Earth became more real when we learned it was not the center of everything. Space became more real when we learned it could curve. Time became more real when we learned it could pass differently depending on motion and gravity. Matter became more real when we learned it was not solid all the way down, but structured through fields and quantum law. A shallow picture can feel comfortable. A deeper picture can feel strange. But strangeness is not a reason to retreat. It is a sign that reality is larger than the first map. Particles sit exactly at this boundary. They are the bridge between the measurable and the unimaginable. We detect them through marks in instruments, through flashes, tracks, clicks, and energy deposits. Those marks are definite. They belong to the shared world of data, but the behavior that leads to them is quantum. It may involve probabilities, interference, field excitations, and states that do not fit the classical idea of a thing moving along one path. So particles appear object-like when they leave evidence. but their deeper nature is not object-like. They are what fields do when the universe produces measurable quanta. They are how invisible structures become local events. They are not nothing. They are not ordinary things. They are something stranger. This realization changes how we understand matter, but it also changes how we understand ourselves. The body that feels solid is built from atoms whose stability depends on quantum rules. The brain that wonders about particles is made from particles that are not tiny objects in the ordinary sense. The eyes that see matter rely on photons, quantum excitations of the electromagnetic field. The thoughts that ask what reality is arise from matter whose foundation does not resemble thought, language, or intuition. We are not outside the mystery. We are made from it. This does not reduce life to machinery in a cold sense. It places life inside a deeper physical story. The universe has produced structures complex enough to ask what structure is. Matter has organized into minds that can study matter. Quantum fields, through stars, chemistry, planets, and biology, have given rise to beings capable of wondering whether particles are things at all. There is humility in that, and also wonder. Because the more science learns, the less the universe looks like a simple collection of objects. It begins to look like a layered reality, where fields give rise to particles, particles give rise to atoms, atoms give rise to chemistry, chemistry gives rise to life, and life gives rise to questions. At the bottom, perhaps, there may be no bottom in the old sense. Fields may not be the final layer. Quantum information, space-time geometry, gravity, and unknown physics may still lead deeper. Dark matter remains unidentified. Dark energy remains mysterious. Quantum gravity is unfinished. The meaning of measurement remains debated. The universe has not handed us a final dictionary, but we have learned enough to know that the old picture of matter as tiny balls in empty space is not enough. It was a useful beginning, not the final answer. The final answer, if there is one, may not be visual. It may not fit into a picture the human mind can hold like a sculpture. It may be mathematical, relational, field-like, informational, and deeply quantum. It may describe not little things, but what can happen, how states evolve, how fields interact, and how definite events emerge from possibility. Our words will always be imperfect, but the imperfection of language does not make the universe vague. It means our language must remain humble. We can say particles are real, but not classical objects. We can say matter is solid, but not solid at its foundation. We can say empty space is empty of particles, but not empty of fields. We can say the world is familiar, while admitting that familiarity is only the surface. This is the calm truth at the end of the particle illusion. Matter is real. Particles are real. But reality is not required to be intuitive. The universe is not less real because particles are strange. It is more profound because what we call matter may be the visible surface of something deeper. Beneath every object is a structure we do not directly see. Beneath solidity are interactions. Beneath particles are fields. Beneath certainty are quantum states. And beneath the familiar world, there may still be rules we have only begun to understand. Good night, and see you in the next video.